Section 11.1 is our first section of two sections on how to find the zeros of polynomial functions and some of the theorems around them. So a function f, we know, let's look at this this example of a degree 2 polynomial. A quadratic function is a quadratic function if f of x is ax squared plus bx plus c, where a, b, and c are complex numbers with a not equal to 0. By complex, I mean they're on the complex number line, but typically we work with real numbers, which are included in the complex numbers. When we use the zero property to find the zeros of quadratic equation, remember the zeros are where our graph crosses the x-axis, so the x-intercept. So, for example, if I of f of x is x squared plus 2x minus 15, I say, okay, what are the factors of negative 15? That add up to 2, well, that's going to be 5 and negative 3. So f of x factors 2x plus 5 times x minus 3. And if I wanted to know the zeros of this polynomial, I would take x plus 5 equals 0, and I would take x minus 3 is 0 to find that the zeros are x is negative 5 and x is 3. This is where my graph crosses the x-axis. These are its x-intercepts. If I have f of x is negative 3x squared minus 2x plus 1, I still need to factor this. I want to first find what are the factors of AC that add up to b. Well, that's going to be negative 3 times 1. And negative 3 plus 1. So I use that to pull the middle term apart because our a doesn't have a leading coefficient of 1 like in the first example. I am going to have to factor by grouping. So I have, let's go ahead and set it equal to 0, negative 3x squared minus 3x plus x plus 1, and then I factor by grouping. The greatest common factor of negative 3x squared and negative 3x is a negative 3x. That leaves me negative 3x times x plus 1. The greatest common factor of x plus 1 is 1, and I still need to pull out that factor of 1. So this quadratic function, or degree 2 polynomial, factors to negative 3x plus 1 times x plus 1. So I take each of these factors and set it equal to 0. I have negative 3x plus 1 is 0. I subtract 1 from both sides, so I have negative 3x is negative 1. I divide both sides by negative 3. I get x is positive 1/3. And if I have x plus 1 is 0, I'm going to have my other 0 as x is negative 1. So this should have been a little refresher of what we've covered in chapters 5 and 8. Now, a quadratic function is an example of a degree 2 polynomial function. A polynomial function of degree n is defined by f of x is a sub n times x to the n plus a sub n minus 1 times x to the n minus 1. Basically, these are our coefficients where I've got x to a set degree, degree n. So when I said a quadratic is a polynomial of degree 2, that's because it's of the form f of x is, let's say, 2x squared plus 4x minus 8, right? This is an example of a degree 2 polynomial. But we don't just have degree 2 polynomials. We've already looked at cubics in this course. Now, I want us to focus and build up to, if we're given a cubic or a degree 4 polynomial, how do I find the zeros of that polynomial? Where does that polynomial cross the x-axis and its complex zeros as well? So we start with the division algorithm. So let's let f of x and g of x be polynomials where g of x is of lesser degree than f of x and g of x is of degree 1 or more. Then there exists unique polynomials q of x and r of x such that f of x can be written as g of x times q of x plus r of x, where r of x equals 0, or the degree of r of x is less than the degree of g of x. We think of this is the remainder, right? And this is the divisor. So let's work through an example of dividing a polynomial and rewriting it using the division algorithm. So I'm going to divide the polynomial f of x equals 3x squared minus 2x plus 5 by x minus 3, and then we'll rewrite this using the division algorithm. So I'm going to take 3x squared, let me scoot that over a little actually. I'm going to take 3x squared, I didn't scoot it over much now did I? X minus 3 divides 3x squared minus 2x plus 5 divided by x minus 3. Well, what do I multiply x by to make it look like 3x squared? 3x. 3x times x is 3x squared. 3x times negative 3 is a negative 6x. Now, if you do not quite remember polynomial long division, I recommend you watch the video before this one in the playlist. That's a refresher of long division. Now I go ahead and subtract. My first terms cancel. Negative 2x plus 6x is 4x plus, sorry, that should have been a negative 9x, which would give me 7x, because 3x times negative 3 is not negative 6, it's negative 9, plus 5. What do I multiply x by to make it look like 7? That's x, that's going to be a positive 7. So I have 7 times x is 7x. 7 times negative 3 is a negative 21. I subtract this. My first terms cancel. This becomes a positive. 5 and 21 is 26. So this is my remainder. This is my r of x. And here I've got my g of x and q of x. So I have f of x, which we originally had as x cubed minus 2x plus 5. We can rewrite that as x minus 3 times 3x plus 7, that quotient, right, that's our q of x, plus r of x, which is 26. Now let's go ahead, I didn't do this in my notes, but let's go ahead and FOIL this out and double check that this worked. So I have f of x is 3x squared plus 7x minus 9x minus 21 plus 26. So f of x is 3x, that's the worst degree 2 I've ever drawn, squared plus 7x minus 9x, that gives me a negative 2x, and negative 21 plus 26 is a positive 5, right? We got back to our original function by rewriting this using the division algorithm. Besides long division, there's also synthetic division, but we can only use that in special cases. So when a given polynomial is divided by a binomial of the form x minus k, we can use a shortcut called synthetic division. So let's again examine 3x squared minus 2x plus 5 over x minus 3. In the last example, we used long division to find that this would equal 3x plus 7 with a remainder of 26. So I'm going to work through synthetic division and example, and then we're going to do a whole lot more examples to make sure we're all on the same page. So in synthetic division, what I do is I take my k, which in this case is 3, and then I take all the leading coefficients of my terms, and then I'm going to do first is pull down this first term. I then take 3 times 3, which is 9, and then I add these two. Negative 2 and 9 is a 7. Then I take 3 times 7, which is 21. I add 5 to 21 and I get 26. Didn't we find a remainder of 26? Well, that's because this last term is our remainder. I also know that because I divided, this is supposed to be x squared, my apologies. Because I divided a degree 2 equation by a degree 1 equation, I'm going to lose a degree. So I have left 3 x to the first power, because it was degree 2, that's a sad typo, plus 7. Well, wasn't this what our quotient was? So we can use synthetic division. It's eventually going to help us determine the zeros of larger polynomials, but I want us to get a lot more practice first.